Welcome to this last video of my playlist about the preparation of benzaldehydes. This video is about the reduction of benzoic acid derivatives to aldehydes. A number of procedures are available that require just one synthetic step and proceed with high selectivity and yield. The reaction, however, is not always easy to perform and can yield benzyl alcohols as byproduct. If no selective reduction can be achieved, an often preferred strategy is the complete reduction to a primary alcohol followed by oxidation to the target aldehyde. On my channel there are playlists about the reduction of carboxylic acids and carboxylic esters to alcohols and about the selective oxidation of primary alcohols to aldehydes. In this video I'll focus on the selective reduction of acyl chlorides, nitriles, amides and esters. Let's jump right into some specific examples. Acyl chlorides can sometimes be hydrogenated selectively to aldehydes in the so-called Rosenmund reduction. This requires an aprotic solvent and a slightly deactivated catalyst. Supported palladium is the most common choice, and deactivation can be achieved with sulfur derivatives or pyridines. Other catalyst poisons are tertiary nucleophilic amines, imidazoles and chelating ligands such as amino alcohols, diols or diamines, but these are not always compatible with acyl chlorides. Aromatic acyl chlorides at least cannot be converted into ketenes, like aliphatic acyl chlorides, but even pyridines sometimes form insoluble complexes with acyl chlorides and should better be avoided if possible. In this example, no additional deactivation was necessary because the starting material already contained sulfur. This here is a procedure for deactivating palladium with sulfur and a typical Rosenmund hydrogenation. First, elemental sulfur was refluxed in quinoline for 5 hours and the product was then dissolved in toluene. A small amount of this solution was then added to a mixture of the benzoyl chloride and the supported palladium catalyst, without any additional solvent. Hydrogen was bubbled into the heated reaction mixture and the progress of the hydrogenation was monitored by checking the pH of the exhaust gases. The aldehyde was obtained in good yield without extensive debromination. Instead of hydrogen, also silanes can be used as hydride donor to reduce acyl chlorides to aldehydes. In this example, around 3% of a soluble palladium phosphine complex was the catalyst and the reduction was conducted in toluene at 40 degrees Celsius. Again, no hydrogenolysis of the arene-chlorine bond occurred. I'm highlighting this because such dehalogenations occur readily and can be difficult to suppress. Also, biareles are often formed when aryl halides are treated with reducing agents in the presence of palladium or nickel. Lithium aluminum hydride can be deactivated by partial alcoholysis with terzbutanol. The resulting reagent enables the selective reduction of acyl chlorides to aldehydes, even in the presence of cyanogroups, as shown here. I'll show you now some examples of the reduction of nitriles to aldehydes. For this reaction, diisobutyl aluminum hydride is the reagent of choice. This reducing agent is highly selective, and even benzyl bromides may remain unchanged in its presence, as in this example. No primary amines or benzyl alcohols are usually formed, even with an excess of DIBAL. The only disadvantages of DIBAL are its high price and the formation of isobutane during hydrolysis, what can be an issue in large-scale preparations. Also in this example, a cyanogroup could be reduced with high selectivity to a formyl group. The reduction was carried out at -50 degrees Celsius to prevent reductive debromination. 2 halopyridines are reactive electrophiles and can, for instance, be readily dehalogenated with lithium aluminum hydride. In this example, sodium hypophosphite was the reducing agent and Raney-nickel the catalyst. Although cyclopropanes are often cleaved by hydrogenolysis, this did not occur here, despite the high reaction temperature. Although Raney-nickel is usually generated and used under alkaline conditions, in this example a benzonitrile was hydrogenated with this catalyst in neat formic acid, which also served as hydrogen source. Despite the huge excess of catalyst, no debromination or deformylation occurred. Formic acid will also reduce nitriles with platinum oxide as catalyst, as shown here. No reduction of the ester occurred. It is not clear if the large amounts of catalyst used in this and the previous example were really necessary. Only few examples have been reported of the use of sodium hydride as reducing agent. Because of its low solubility and strong shielding by solvent molecules, hydride usually only acts as base and not as nucleophile. In the presence of the Lewis acid zinc chloride, however, sodium hydride can reduce nitriles to aldehydes, as shown here. No hydrogenation of the allyl group occurred. Carboxylic esters can sometimes also be reduced selectively to aldehydes, but over-reduction to the alcohol is common. In this example, a methyl benzoate was reduced with a slight excess of DIBAL in dichloromethane at -78 degrees Celsius, and a fair yield of aldehyde was obtained. No debromination or reduction of the cyano group occurred. The selectivity of this reaction can be enhanced by Lewis acids. In this example, the ester was activated with 2 equivalents of an aluminum amide. Then, with just 1 equivalent of DIBAL, simple alkyl benzoates could be cleanly reduced to aldehydes. The choice of solvent seems to be critical in ester reductions with DIBAL. Reductions in dichloromethane with just a small excess of DIBAL and at -78 degrees Celsius can give good yields of aldehyde, as shown here. In THF and with a larger excess of DIBAL at -35 degrees Celsius, however, the alcohol became the main product. Carboxylic acids require some activation to enable selective reduction to aldehydes. Anhydrides can be hydrogenated, but the reduction often stops at the stage of the acylated aldehyde hydrate. For instance, hydrogenation of acetic anhydride can give good yields of 1,1-diacetoxyethane. In this example, 4-cyanobenzoic acid was activated as mixed anhydride with pivalic acid and then hydrogenated with a soluble palladium catalyst in THF. A high yield of the benzaldehyde resulted, without any hydrogenation of the cyano group. I will show you now some examples of the one-step reduction of amides to aldehydes. This is another rare example of reduction by sodium hydride. In the presence of sodium or lithium iodide, some amides can be reduced selectively to benzaldehydes in good yield and under mild conditions. Sodium iodide is probably just acting as a highly soluble Lewis acid and, by increasing the polarity of the solvent, as a solubility enhancer for sodium hydride. Some years ago there was a flood of papers about the use of large amounts of lithium perchlorate to promote all kinds of organic reactions, and sodium iodide could have similar properties. Interestingly, amides are reduced faster than ketones by sodium hydride. The ketone in this example was perhaps deprotonated to a sodium enolate and thus protected from further nucleophilic attack. In this example, a pyridine ring was first metallated by sodium hydride through chelate formation. Upon heating, this chelate rearranged to a nicotinamide, which was then reduced by sodium hydride. Another suitable reducing agent for amides are silanes in combination with a Lewis acid. Here, a benzamide was reduced with a silane and titanium isopropoxide at room temperature. Few examples of practical procedures for the reduction of trihalomethylarenes to dihalomethylarenes have been reported. Some electron-deficient trichloromethylarenes undergo, however, a remarkable aromatic substitution that can yield benzaldehydes. In this example, trichloromethyl nitrobenzene was refluxed with 1 equivalent of sodium methoxide. A mixture was obtained of the expected alcoholysis product, a methyl benzoate, and an unexpected product, a methoxybenzaldehyde. This unexpected aldehyde was formed by vinylogous displacement of chloride, followed by re-aromatization and hydrolysis, as sketched here. Let's have a look at some potential side reactions. As mentioned, a common side reaction of the partial reduction of carboxylic acid derivatives is the formation of primary alcohols. The reason for this is that aldehydes are much stronger electrophiles than most carboxylic acid derivatives and are quite easy to reduce. And in the presence of hydrogenation catalysts, benzylic alcohols are often reduced to toluenes. Then, in the presence of metals or other strong reducing agents, aldehydes can also dimerize to pinacols. Strong bases and nucleophiles can also promote Cannizzaro-type disproportionations. Therefore, these reactions must be monitored carefully and stopped as soon as the starting material is consumed. Here are some further, mostly recent examples which you can also find in the description of this video. That's it. I hope you found these 4 videos useful, and good luck with your own organic preparations.